So we are starting to record. That is what was taking up a bit of time. So yeah, in case you, it is good to see you. I never turn on my video. So we are not getting you. You are muted. I think someone was joining and I got muted. Sorry. Let's welcome people to the meeting. So I'll just welcome the, I don't know, I'll continue. I stopped Budechani Nakavugo, Mwanja Charles, Sogola Ronald, who is there twice, Haga Erios, Manyema, Akwede Stera, Rodela Nambi Faith, Litunji, Mawaji David, Vianney Green. Who is Vianney? Napambros, Kalimba, Ian Ken, Julius Kagango, Prince Wang Okinovich, Mabnan Dons, people have changed their names. Namugwanya Patience, Alionzi Lawrence, Dodwa Faruku, Kutosi Robert, Ivale Wycliffe, Matanda Pius, Eva, Manuel, I don't know what the name is, Mwezi Kendi, Muhereza Lotel, Mwezi Bob Robert, Chencha Sam, Teje Chirojas, Nicholas, Sendikwanawa, Helena Tukwase, Mjisha Timothy, Navidia Sharifa, Bradley Tumwine, Jude mentioned, Kwirija, Joshua Saban, Masubaron, Crazy B, Emmanuel, Okay, I think he's the one who muted my microphone as trying to pronounce his name. Esther Patricia Nyabel, Mulunchi Marunga Bernard, Haifa Karuki, Samuel Kalumba, Paul Triahavwa, Muhindos, Happy Edwin, Mkwad, Israel, Megade Israel, Mukashaba Godwin, Jordan and Ariana, Okede Benjamin, Kasozi Mike, and Alexander Mwanga. With other people, Namiri, and Kule Mujungu, I don't know. So I'll be off video for some time anyway, having a bit of a cold. But I'm also going to be presenting, so at least I've seen you guys. You're very welcome. Last time we had so many issues, so we just almost went right into the meeting. So we'll have an opening prayer. Who is going to pray for us? No, I've not yet figured out how to switch screens. Helen, can you pray for us? Okay, Stella, can you pray for us? Are you there? Mary Patience is going to pray for us. Thank you.
Heavenly Father, we want to thank you that we are here today. We want to place the works of our hands and minds into your hands. Bless us with a clear intellect, sound judgment, and retentive memory, and may this class be a fruitful one. Amen. We can now proceed with the lecture.
Amen. Thank you, Mary. I need to figure out how to switch between screens. So I can't save one. I just have a sample, but I can see this. So we're going to continue today's lecture with the last time we looked, actually before we broke off, we looked at photoelectric effect, and you should be able to, first of all, identify what the experiment talks about in terms of what it reveals about the nature of light. You should be able to, of course, describe the experiment. You should be able to know the classical expectation and that phase, and how quantum physics is able to explain it. Then today we're continuing with mostly Compton, because let's say we had that recap of the photoelectric effect. So we're going to do the Compton effect, and the Compton effect is it reveals the particle nature of radiation, or the particle nature of waves, if you want to make it as simple as possible. So then, close to that is this gamma experiment. So the Davison gamma experiment is much easier than the Compton effect, than the Compton experiment. So the Davison gamma experiment, it's much simpler, but in terms of the setup, but it's a sort of explanation. So it's a slightly different explanation. I don't want to call it more complicated, but because they are both experiments. Now, I'll just share starting right now. Present a window. So we're going to do a derivation today for the Compton scattering. So we said that the Compton scattering is the reverse of X-ray production. So X-ray production is very straightforward. Electrons hit a target, a metal target usually, and then X-rays are emitted, and you can see the image on the left. So those are the used to do a lot of your imaging. We know that electrons absorb X-rays, and this energy, of course, bonds absorb the most, so that they show up in these images. Then the rest, so you're really creating a shadow using these X-rays.
kule. Stella, where's Mark again?
Which I don't know.
Would you?
I've lost my Wi-Fi adapter, but let me just work on that briefly. Oh, okay. So I think we should be back for everyone.
Hello, sir. It seems we can't hear anything.
Sorry about that. As I see, it mutes occasionally when I stop presenting.
Being my earphone, sorry.
Why did you stop listening?
From the start. From the start.
What is the start? What is the last thing you heard?
Nothing.
Nothing, just.
Oh,
Start
you
from the
said
point where I started explaining the experiment.
Caption. It was caption discovered that when a beam of X-rays of alpha intensity is scattered through an angle grabbed one by sending radiation through a metallic foil, the scattered radiation contains a component of well-defined matter, which is no longer that, and that phenomenon called diffraction effect.
Okay, so just go back, you can turn off your microphone. I don't know who is joining in via phone, but I think I've switched off the mic. That's good. Okay, we continue from here, really, because we said that you have this X-ray wave, which I'll not attempt to color again, but so this wave would be similar to that which goes through your body when you go to the hospital. And then we said that if you look at this classically, you have the three wave properties. You have wavelength, you have wavelength and frequency, you have speed or velocity, and you have intensity. And then, so those are the three main ones. From wavelength, you can also look at frequency. Those two are the same. So what defines a wave is characteristically mostly its wavelength. Now, what you expect to be absorbed is intensity. So this is classically you'd expect this to reduce. The intensity is like the brightness for your light. So you just expect this wave to emerge on this, but on what? But of less intensity. Or, of course, if you have another material like glass, it affects the velocity. That's why you have refraction and what. So this is what you expect classically. Classically, you expect the intensity to what? Then quantumly, something else happens. You have this changing. You have the wavelength or the, so that's a bit, you have the wavelength or the frequency changing. So this is quantum. What has happened to my free forms? Yeah, that's just quantum. Now we said that we have looked at Einstein's work in the photoelectric effect, and we are saying that light is made up of different particles, which are, this wave is made up of different packets, which are called photons. I think we need a big marker. So what we see that this is a carbon or graphite material. So when X-rays hit this, they easily okay. The electrode is bound, so you need some energy to set it loose. Now, you remember in the photoelectric effect, you don't need a lot of energy, but that's not the discussion now. So, what's this wave here? Classically, you'd expect this wave to what? To emerge on this side. So, with a reduced intensity, expectation. You'll excuse the typos. Biggest intensity, right? So that means same what? Same frequency or wavelength. So this is the classic expectation. Now, at the quantum level, we have an interaction between this wave and the electron or the particle. So let's just have Trump orange for this electron. I don't text. I want the pencil. Okay. I think I have to first get out. So we have this electron here. So we'll just make sure that the wave interacts with it. And so you have this scattering. Maybe we can have the electron somewhere here. Let's first continue with this wave. So you have this scattering here at this point. Now, I don't know if you've ever tried to shoot mangoes, or more graphically, if you've seen a car accident or been in one, or a boat accident. So what happens is that things are scattered. So, and that scattering can only occur if there's a particle in here. So, and we have said that because classically this will just fade, it will just reduce in amplitude. So if you had this intensity here as I1, and then this is I2. So among the things we didn't look at there is amplitude. Amplitude is important as well. So that means there are 4 attributes. But intensity is the collection of waves. So it's not really, it's what was throwing me off track. So amplitude is so this is actually amplitude, not intensity, since we are doing the recording. So intensity is the number of waves. It is number of waves. So it's the number of waves of that same characteristic, what we'd call coherent. So this is what you have. either expect this a reduction in amplitude or a reduction in what? In the intensity, because intensity, if a reduction in intensity means essentially that some of those have been absorbed and they're no longer available. So if you had a torch, you'd have a smaller beam on this side, but it will still be the same light. Now, borrowing the analogy of the photoelectric effect, imagine if you shine blue light at this, and then you end up with two colors. Okay, this is red. So you end up with red and another color, let's say green. Now, that can only be due to a wavelength shift. Of course, X-rays have, they have false colors. They don't have actual colors. But so this would be very strange if you encountered it for the first time. If you shine red light here and then you see red and green, that would be quite disturbing. So now that corresponds to delta lambda. So in case you have this as lambda, and then this is the scattered radiation, lambda prime, this is still lambda. So delta lambda is lambda prime minus lambda. So you have this wavelength shift, and this delta lambda here is the what? It's the Compton shift. So I hope that bit is there's enough information, or it's clear enough.
Pardon, so on the what you've written in green, print in lambda.
Compton shift.
Thank you.
Let me just type it in. Try to avoid that. Something that should pin the screen, but you guys can do the pinning yourselves. So to prevent when somebody speaks, they come to the viewer. So you can just pin it. Okay, to that one. So this explains everything. Let me see if I should save this. Bitmap should take up less space. Control Shift. I definitely can't save to this PC. Just save it to the desktop. The way is to open another application. Good. You'll probably be seeing something blank later on. It is still showing the same window. There's a way to pin these meeting controls. Let's see what error this is. Okay, let me first stop sharing this. Then we share. Share window. It should be shown up here. Good. So we have looked at this whole background, and we've seen that we'll look at diffraction later on, but you remember seeing this bit here. So this is this crystal here. So what you'd expect is that this would come in at this angle. You guys know, maybe in this bit we should add, gosh, there are so many others. So we add amplitude, and so we're going to add phase. Amplitudes. Phase. I'm not showing that one, sorry. But it's the diagram we had. So phase is the angle. It can be related to the frequency as well. 2 pi, you have omega is equal to 2 pi f. So you have angular frequencies. And so there's this phase shift. The frequency also corresponds to a phase shift. So where you had this coming in along that line, you have that shift as well in terms of angle. And okay, there's the particle acceleration to this change in angle. Like if two bodies collide, they are going to move at different angles. But don't worry about that for now. This is a phase shift. Now, what happens is that this electron is not lost. It doesn't like fly out. So that is why I was calling it a high energy electron. So what happens is that it recoils. Like it's like if you shoot a bullet, the gun moves, but considerably to the direction of the bullet, to the how much the bullet moves. You have what you call recoil. So recoil is like a small shaking. So if you had a weak, or I mean, it's not high energy. It's a loose. It's a high. It has a high binding energy. So it is not. It is not. So it scatters this, but it's also possible that it's what? It's able to move in a certain direction. But we're looking at mostly this wave shifts a lot more. So that's why you see the word recoil there. Now there are different shifts, but you have two distinct peaks, one for the incident and one for the scattered. We're going to see why. Let's go back to this bit. So I briefly talked about the wave model prediction. We've talked about so in the wave model prediction to recast, Okay, I think that's okay. I was hearing myself through the other device. So to recast this, we said that this would behave like an antenna. So the frequency at which the electron oscillates would be the same frequency. So the electron will just radiate that, it will absorb some energy and then radiate the same energy, the same frequency, same wavelength, same, only like the amplitude or intensity would be affected. So in the photon model prediction, or where you see photon model, sometimes you have quantum prediction. So now we've already talked about this. We imagine it as a collision of two particles and the electron is initially at rest. So the scattered photons fly off at different angles, phi, and so they lose some energy, so you're going to see that delta lambda or delta F. So we already know, okay, we haven't looked at it yet, but the momentum is given by the energy divided by the what? Okay, the momentum itself is from the de Broglie hypothesis. So you remember, we didn't talk about de Broglie hypothesis yet. So lambda is equal to, if you look at this bit, the wavelength is given by the momentum divided by the Planck's constant. So that is de Broglie's hypothesis. Now from de Broglie's hypothesis and from this energy, this is classical Planck, is equal to HF. That was postulated by Planck. Einstein is equal to mc squared. So from these two, we'll be able to sort of see mathematically what happens to this. Now, we have said that so what you see here is an electron recoiling with a certain momentum. So it is the wave which is scattered. Most people they say that the electron is scattered, but so it moves, but there's a momentum change for the electron. So it's initially at rest, and so there'll be a tendency for it to move in a certain direction as it is recoiling. So that is the momentum. Now, gosh. Here is there we are. There's an English saying which translates to OMG. Let me just check that the audio is on. People are quiet. Maybe they're paying a lot of attention. Amanyere, are you still seeing nothing? I'm seeing that in the chat.
Yes.
But I have a second screen and I'm seeing a PDF with an equation there. So you might need to check your device. So I see the advice is to pin the screen. So we're using another account. So you look for Masu Baron, but you should see like a screen. So you can pin that because every time there's any activities, another screen comes on. On this side, I'm seeing captions.
I've got it.
Part of the recording.
I've got the thing. I've got the screen.
Okay. So it looks a bit yellower here. So the next bit is to derive this equation here. That one which I've highlighted. For some of it may show up slightly delayed, but that's the equation. So that wavelength shift is what we're trying to get or to derive. Now, there's this explanation in here. So there are a few things we need to talk about. I think I'll just take this to paint. Select. Let me see if it's working. Not working. Let me print screen.
I think it's not working.
I was seeing if I can. Let's add this image. So I'm trying to look for something like highlighters. I see text marker. Okay, there's a pencil here. Good. You guys will see the pencil later on. What is it showing black? What do I feel like a black thing where this notification is supposed to be? We have moved out of the way because it's showing up here as black. So I've just moved the diagram out of the way. So this is the incident X-ray, right? But I wanted to do this in paint so that it's persistent. So this is your electron here. OMG. So this has an energy E, right? So it initially has an energy E, we should denote with EE. And so now, okay, we'll have to talk about rest mass energy. We can't avoid it anymore. Rest mass energy is the square of rest mass energy is the square of, so the total energy is the square of rest mass energy plus this momentum shift or momentum change. Now, this expression is derived in another chapter. So we have E squared. Let's go to paint. Paint. So I'm going to stop this briefly and then first go to paint to make this point. So let's first stop. Present a window. Yep, there. So it will show up there. It can be confusing. So this is what we need. You can, by the way, zoom in on your device to the diagram there. So I'll just leave this bit here. So this is paint, it's no longer the PDF. So we'll remove this sharing stuff. Now, we need to just take a note of something else that it's usually easier with a rectangle. Let's use green. Now, this was the relativistic energy and momentum relationship. So you have, can't use text directly. The total energy is given by the rest mass energy. Let's just have a text. Rest mass energy was determined by Einstein. His famous relationship is equal to mc squared. Mc squared. And then you have the what? Momentum change. So that is the equation that you're seeing there. So this is the strange bit, the only strange bit which is there. So the rest of it will just use the laws of physics that we've come up with, we've come across. So we're going to use another resource now, but before we do that, let me just make sure that we're on the same page. So this has initially energy, EE, first erase this. Energy E, subscript E. Yeah. So it's to denote the electron. So of course, this has E is equal to Hc over lambda, and this is E is equal to, this energy is equal to what? Hc over lambda prime, right? Anything else we need to know? So initially the energy of this is 0. So I'll just circle off, I'll just say the initial ones as green. E is equal to, so this is the initial condition. For the electrode, its energy is equal to 0. Then initially this momentum here is P, and initially, of course, the momentum of the electron is, who can guess? It's also 0. And then finally,
it is also,
yeah, finally, this is the final situation here.
It is 0.
So the momentum becomes P prime, the energy becomes that, and then the energy changes by this relativistic thing. So it's mc squared plus pc squared. Mc squared. So this becomes squared plus pc squared. Square. The charger. So yeah, that is what we have. So there's that. It's really a form of conservation of energy, but that is the only strange explanation. So initially you had, of course, initially the rest mass energy of the electron is just, much as we have said it is 0, it is just what? mc squared. Because this P is, the momentum is 0, but it has rest mass energy. Just send this person a message because I can't pick up. So sorry about that. Yes, we have said that we need to probably put an asterisk here because it is not actually 0. It is, so initially you have but we have this is becoming bad. So we have this rest mass energy E, which we can call E naught, which is equal to mc squared. Now, sometimes we add an E here, so sometimes we'll add an E here to just clarify things a bit. So that corresponds to the what? To the electron. So we can just put the electron in purple. And then this other stuff is for the photon. So this is what the energies look like here, initially. Yeah? And then the other bit is the momenta, or the momentums. So momenta, you have photon. So initially the photon has momentum P. Initially it's not easy to write. P, and then electron has 0. It has the momentum. Then finally you have P prime. Electron has what? It has PE. So this is, okay, all these are vectors. So you give them their heads or their tails. I don't know what you guys call them. So you have this conservation of momentum. So you can actually, you know what you start with, you know what you end with, so the rest has to be taken up by the electron. I'll just highlight it briefly and remove the highlight because it can be confusing. Now, but maybe I can just put not over highlight stuff. Unless I put it in a box that is more relevant. So you have, this is known, so you can find PE. So if you call this equation 1, then we can substitute for equation 0 here. No. Let's call this equation 1. Then this becomes equation 2. So you can substitute for 1 in 2, and then rearrange. So you have PC. Now, for you to substitute for this, we have to square. We have to square this energy here. Let me use 1. We have to square. Find a way to get to this. So there are many steps which are being carried out. So that you don't get lost, you square that. So you first rearrange this, and then you square. Let me see. So I'm just trying to get some space here. So after rearranging, let's use E becomes PC plus MT squared minus what? P prime C. So that's our equation 3. And then we'll square this. And then substitute in 1. So this is what you see here. So this whole thing here will be squared. Let me just highlight it. So this is what is going to be squared. So once you figure that out, then the rest is easy to squaring that one. No? Then now you remember I had this equation 1 here which is squared. So we just substitute it for there. So there's another. So that is this step. So we can call that equation 4. So the rest is, so after squaring this, we can substitute for PE. We know that PE as a vector is going to be the initial momentum, which is P, is equal to the final one, which is P prime plus initial is equal to final. So initial is equal to final, and let's just save this. We take questions.
Compton shift.
So we're going to go back to the book. I hope people can admit themselves because I keep saying these things, or somebody is admitting them. We're going to go back to the PDF and then finish up our math. Now, we have, what do you guys call him? Let me just have another paint window. And I'll share that bit. Again, we'll print screen. Present window. And
COVID.
So you should be able to see that now. So I'll just need to erase this. No, let me not erase it. But let's do some interesting things. Okay, I think we have enough space there. Yeah, no. That's not what I wanted. Actually, I wanted to. So that capture is still valid. I just wanted that. Yeah. So you guys remember your physics. It's not physics, it's math. You did it in O level. Where you have that, we call it the cosine rule. So if you have three angles and, three sides and an angle, you see that from the cosine rule. Let's use another color. Cosine rule. Three sides. Does anyone remember Aaron's formula?
Cosine rule.
Actually, we have two sides and an angle, not three sides. But so we can get this PE. We're trying to get PE. It's really two sides and an angle. Because we're trying to get the third side. So the third side here is going to be given by P squared plus P prime squared. So square that, and then also square this. It should look like a P. And then the cosine of this angle cosine of this one. So this is the expression which you have here, which gives you PE squared is equal to P squared plus P prime squared minus twice PP cos phi. So that is really cosine rule. So I'll just add the word equal to that. So we use the cosine rule to get that. So after using the cosine rule, we substitute it back into our equation. I'll use the soft highlight, substitute. I think it was equation 4. Into our equation, what? Substitute. There you have it. So once we substitute back into equation 4, yeah, equation 4 is actually here. Go equation 4. Equation 4. So now equation, okay, this one we already had it as 5. So that becomes equation 6. So substitute that back into equation 4. Okay, they have joined. So this now means that we are done. So where we see PE squared, we substitute it with this. So we're going to have some interesting equation with must multiply by C squared. So PE squared, C squared is going to be equal to P squared, C squared plus P prime squared C squared minus twice P prime C squared cos phi. So that is what happens on this side. Side area. No, not be clear. That's what we have done here. And then after expanding this side, it's gonna be crazy. So let's make it crazier. So once you square this side, it is very easy to square 3 terms, right? All I need to do, no, but I can do it here in Paint. Everything is going to be squared. Then we're going to subtract twice the product of the two. So let's be creative. Let's be creative. Oh, we have space. No. So I'm going to multiply that with that. We need the space right now, so yes, sorry. Okay, I think that's enough space. So I'm going to be in that black box. So the square is that times this. So multiply PC times PC gives us P squared, C squared. This is just an extra step. You guys should be able to do it. Then PC times negative PC becomes minus. So that will be P times P prime, but also with a C squared plus P M C cubed. Then we'll apply through this second term. So it will be minus P prime PC squared plus P prime squared now C squared plus what? Minus, sorry, P prime C. Okay, let's do the M C squared. So that should be clear enough. So you already had this this other side here, which you can expand out. Oh no, sorry, I have one more term. It is M.
The last time that you've written, I think
MPC. Yeah, so we have one more term, MPC cubed minus M. Okay, I've just the M first. Usually I've been starting with the term which I've been multiplying with, if you've noticed. So now it is weird to write MC squared and then P at the end. So that's why I'm putting the P's and P prime there. Then plus M squared so you can write it as M squared C squared, or you can write it as M squared M squared C to the power 4. So you guys like crossing out terms and what? So already you can see that this term and that one will cancel out. Okay. So it will be equal to that second part plus M. So we also expand this bit. It gives us M squared C to the power 4. So from this you can cross out your terms. That and that. Then you had that and that. Then you had that and that. So I'm just doing this for the video, but I'll remove them before I save this because they just look weird. So after crossing that out, we have killed an innocent person. That is the one who was supposed to die. So you end up with this. So this becomes twice PPC. Then you have this this MPC prime. So in this bit, we are saying that this C squared is everywhere. So if we had eliminated it first, even before squaring, you see that everything has a C. So you could have first eliminated that before you square to make your life easier. If you can factorize it out, not really eliminate it. So that once you're doing the multiplication, it becomes much easier. So that is the first thing. Then the next thing is to divide through by this product, PP. PP could mean something else now. But yeah, that's what you have. So you end up with, you remember this had a 2 somewhere. So that becomes cos phi. So all the terms which have PP become 1. So that becomes 1. And that bit you will do because I don't see how to realistically do it here. So it is just that one more step. Yeah, so this can be confusing later on, this purple bit. So that is what we have. So just stop and then go back. I think you guys should be able to see the PDF now, right now. So in case you've just joined us, we have reached this point now of this equation, of this derivation. And the last bit is to substitute for what? De Broglie hypothesis. P is equal to H over lambda. So let me first save my JPEG. Open Shift 3. Are you guys having fun? I hope you're writing somewhere so that you're not just doing staring work, you're participating. To say what? I think that was. I just feel kind enough to do this thing, so kind enough. Sometimes, but kind doesn't necessarily mean good, because it will deprive you of your. So actually, I go through it. My kindness for it. Yeah, I'm presenting to everyone, that's fine. I just have been misusing space. I've been misusing space here. Who has time for that? So we don't need that. Let's see the important bits from here. So we copy this guy here. Let's have a demarcation. Sorry. So, what? Okay. Yes, we want this as well. No, that's not the right rectangle to use. So we need these equations here. In this particular, in the way I list them. So we have those two equations from lambda is equal to h over p. So we can just put text here from the Broglie hypothesis. Where's my lambda? There's no lambda here, so we'll just use the inverted one, which is the y. Do you guys really want to do this? There used to be a shortcut of just flipping. Ain't nobody got time for that. So let's make sure everyone is happy. So to have a lambda there, but it's an upside down y really. So from the Broglie's hypothesis that lambda is equal to h over p. So we'll substitute these two in here. So I do not have. Okay, let's focus on what we have. So MC, no, it's too thin. MC. For the space, we'll use it. MC. Then, so you invert this. 1 over P prime becomes lambda prime over H minus MC lambda over H is equal to 1 minus cos cos with an S. So I think even the last skeptical person is convinced. So multiply by HC over lambda. Since when I just put the text. H over MC. So it leaves us with lambda prime minus lambda is equal to H over MC into 1 minus cos pi. Now, sometimes you see this M naught, M. What is this mass here for? Anyone remember? So sometimes you have M naught, which is rest mass. Sometimes it's ME, which is mass of the electron. So you might see some variations of that. But delta lambda, I'll do better than this. Delta lambda is equal to lambda prime minus, and that is what you call the Compton shifter. So that's what you call the Compton shift. We can pause for questions.
Professor, Mr. Mark.
Yes.
Like more light on this graph.
Which graph?
The graph on page 1271.
Yeah, but there are questions on this bit because I think it's. Are you saying this graph?
Yeah, that graph.
Okay. Remember, we said that initially we had X-rays with a frequency or wavelength lambda naught or lambda, right? And we're saying that due to the Compton shift, you have those with lambda prime. Now, this is, remember you had your electron, so this is the incident, and then this is the detected side. So this is on the detected side. So on the detected side, you have this intensity and then this intensity. So most of the intensity on the detected side is due to the scattered photons. If you try to have that same graph on the incident side, you just have that because there's no Compton shift on this side. So this part here would not be. So this is what you have initially, then it turns up to these two peaks of different intensities. So realistically though, you'd have something like this, because if you to match up the intensity, that would draw in a straight line. If you're to match up the intensity, if you're to match up the intensity, it would be something like this. So you guys can right there. But let's see. No, it's not important, but you'd have something like that. So that I'm just going to draw a line there. So this intensity is here. If you try to compare these two intensities, you'd have something like this on the before you reflect and after you reflect. So at this boundary here, you'd have this would be the graph on this side, this would be the graph on this side after the Compton scattering.
I get it. Thank you.
Okay. So that would be it from Compton. OMG. So the second experiment, which we'll do after like a 5-minute break, is Davison and Gamma experiment. I think scroll so much. I think we'll take a small break. Either take a drink or something. During that break, of course, I'll stop recording so that record again. For those who want a productive break, maybe I'll just leave the screen on so that you can go through that example. As I said, there are many questions in this book and online, so you can go through a number of them. Yeah, I'll go through a number of them. Okay, we'll
Can
meet
we
here.
have one example? To have one example related to what we have been doing and
okay, yeah, we'll have an example.
But they're clear. Examples are clear.
Yes.
We'll have an example, but I'll not solve it like what you're seeing in the book. I'll just highlight a few things that you need to watch out for when you're dealing with these problems. Yeah. Okay, we'll be back here at 11:40. Okay, I'll be
What
back.
time are we going to end the session?
I thought midday.
Okay.
Yeah. But 4 minutes, you. So I'll turn off my audio for now.
Aaron. Aaron.
Because I was thinking, oh, we do uncertainty principle. Okay. How? Oh, God. But when are you doing uncertainty principle? How is it? Shall we do uncertainty principle?
Excuse me, your microphone is muted, so I cannot hear anything.
Oh, we are not hearing.
Nothing, as in nothing. I'm hearing nothing.
We explain, but we are not hearing.
Oh, okay, sorry about that. I'm switching between this. I got muted somehow. There's a bit of background noise, so maybe that is confusing. I can identify the culprits, but it seems I've left the phone somewhere in the corner. I think that should be better. I managed to mute the sound. So I said that for most of these questions, it is trying to see if you can identify the wave shift, the compton shift. And the second bit is trying to look at this angle. Can you be able to, for example, if you use things like maximum and minimum, do you know what that means? Do you know what angle is maximum, as in, because you see it is 1 minus, so that means as the angle is increasing, the cosine graph itself, you should have intuitive picture of it. It starts off for it at maximum, so then it is maximum again at what? So it is maximum at 0. And so this is 90. That is 180. This is not as good as paint. It's not that I'm writing badly. It's not as precise. So you have 180 which is negative, then you have 360 where it is complete.
Green.
So what would be for you to get a maximum here, so you have to be careful about this negative here. Because you're subtracting. Now, interestingly, cos 180 is negative, so it makes that value positive. So maximum shift, you're looking at that angle being what? Like 180. Yeah? Of course, 180 and negative 180 are the same thing for this case. Okay. They should be the same. So once the angle becomes negative, then that is when you have maximum shift. And okay, not really negative. The angle becomes when it is 180. And what does 180 mean? It means that it is a reflection. It's almost like a reflection. It's just a 180-degree turn. But so the bits, can you tell incident and what? So sometimes people are used to being given the incident, sometimes you're given the scattered one. So can you work backwards? Go with you. So you need, so sometimes you need this equation, sometimes you need some of the expressions that we have derived. Inside this. Like that. I hope you've been on the shared screen. I just saw the video I've been on as well. So yeah, that is the gist of the questions. They'll be trying to. So you have to first of all determine. Can I determine delta lambda? If not, the angle. If not, do I need to go back to the first principles, determine what the momentum is and what? So if you can't use the sequence, you may need to go and see what is the momentum, what energies am I working with. These questions are those which give you energy, and so you have to use those two relationships. Lambda is equal to h over p, which is De Broglie's hypothesis, and then E is equal to PC or MC squared plus PE squared. So yeah, so energy of course is going to be different from, because you see is equal to hc over lambda. So maximum energy, okay, energy is going to be inversely proportional to wavelength. So if you have of course, if you have a big shift, then you have a big change in energy. That is even if it's inverse. So yeah, a few of the things you need to navigate through along those lines. So in this question, we're using the relationship between angle and wave shift. Okay, let's first go to the beginning of the question. You use 0.124 nanometer X-ray photons in the Compton scattering experiment. At what angle is the wavelength? And at what angle is the wavelength of the scattered X-rays 1% longer than that of the incident X-rays? At what angle is it 0.5% longer? So what is the initial one? Lambda. You not put a subscript. What is the scattered one? Lambda prime. So what is the 1% difference? X plus. Some people usually add 1. Okay, it's funny now. It's 1 over 100 of X. So 1 over 100 of lambda. So you work with that, and then you get the angle. So for most of the Compton questions, it looks like you don't have enough variables. If you're to look at it from the first bit, it's like, okay, 1%. 1% is also delta. So you quantify that. So even if so you need to have these two wavelengths if you have the percentage. You can just use the what? There's something also called the Compton wavelength. This is
Mr. Sorry to interrupt you a bit. There is where I talked about cost being negative.
Cost being negative what?
There is where you talked about
that
you should be and I really didn't get you.
The rules of Aaron, and then you in that. So that is the shared screen has. Did I turn it off instead of hiding? Can you first stop sharing and then share again? It seems to be a general problem. What video you have it, Jacobs? So we're there. Okay.
Excuse me, Professor. I'm seeing better now.
Yes. So that, I don't know if you saw the course. So the course is negative at this point, so it turns that expression positive. So these are some of the most interesting things that you'll find on this Compton shift. But so for some of them, you to go back and say, okay, what is colliding with what, which is longer, which is shorter. So usually the incident, the scattered one is longer. As you saw from that graph, it shifts to the right in terms of wave. So it's gonna be longer. So there's what is called the Compton wavelength, and that Compton wavelength, when that cosine expression is zero, and that cosine expression can be zero. No, when cos phi is zero, yeah, and cos phi is zero at 90 degrees. But it is not really. So delta, that Compton wavelength is given by h over. It's just that those constants. Saying it is when cos phi is equal to 0 is just an oversimplification. It's like cram work, but it's when h is equal to, it's that constant there. So sometimes you see as delta lambda is equal to lambda c minus so when you see that, don't say Mr. Mark didn't teach us these things. So this is called also the Compton wavelength, being given as the Compton wavelength, and it has a value. What is that value? It is, I think it's this value which they're referencing, 0.124 nanometers. There are sometimes when we choose to give the exam, you're given the constants. In the test unit, actually, there's still a very big dilemma of how to examine you guys on some of these things in relation to what the exam might look like. So we'll see, maybe you can have some homework, because it is hard to convey some of these on the platform. So that said, I'll be enrolling you guys. Part of the reason is I wanted people to be engaged, and also for your class reps to be aware who is with us, and maybe try and reach out to people and see what, in case there's something happen. But in case you know anyone who is not able to continue at the moment for various reasons, one, it is important that you keep in touch, that the person keeps in touch, because there's a very big temptation to be like, some people may not want anyone to know that they're having a dead year, but it's important to keep touch with your classmates. And of course, once you have what you call a dead year, you're going to have also new classmates. So it's also important to keep in touch with them. A few other things that you need to be concerned about. That part of that is your well-being. Because most of the people are like, they're concerned with explaining, like, or not explaining, but with the implications. People trying to see that. Most of the time, it's people trying to explain that, you know, I had a dead year, I'm not retaking, things like that. But you also have to become an integral part of the year you're in, or the cohort. So let's say Ronald is my friend, and so you're still friends. That doesn't change, but you also need to have a good connection with the people you're doing the course with at any one point. So that came up. What you should know, especially in these times which we're in, it is likely to be more prevalent than usual. So that we'll look at the Compton, the Davidson-Gamma experiment. I think I don't remember actually if we looked at Bohr, because I mean at De Broglie's hypothesis, because in my recollection there's somebody who was reading from that, but I know those two, De Broglie and Bohr, are alike. So, but in any case, we've talked about it many times. So when we looked at Bohr, we are not really looking at De Broglie in this case. So that means probably we will be previous. No, it's the same chapter. So in the Compton experiment, we have seen that photons can behave as particles, or photons have that particle behavior. Now, in this case, we are seeing particles behaving as waves, and the particle of interest, maybe a series called person of interest. I don't know what it's about, I just know the title. But so in this case, the particle of interest is the electron, really. From the Boy's hypothesis, all this, we'll see later on that it applies to all matter. And we are going to, I just have a feeling we've done this, but I don't want to commit to it. Now, hyperphysics, I mean, sorry about hyperphysics. Hyperphysics anyway has these diagrams that we have these are from hyperphysics, Zeno and hyperphysics in hyperphysics. So these are hyperphysics. So in the Davidson-Gamma experiment, so these notes were made with, since we are referring to them, the main notes, I just added these things from these two books earlier on, but most of this language is from Professor Lubujo. When we taught this course with him, he had a number of notes. And if we had a glimpse of what would happen in this year, then, but we digitized them with him. There have been some changes to the diagrams, and probably there'll be more changes to them, because I think you noticed they had some few glitches, some few errors. So the Davidson, you know that Davidson and Gamma we are working with, let's first go back to this hyperphysics. They're working at Bell Labs, and they were studying nickel, and Bell Labs is in the US, where you have, I think now it's Nokia Bell Labs, but we had a number of inventions from Bell Labs, including the transistor. So this was in 1927, and you had these two scientists working on studying electrons, and they were directing them to a piece of nickel. And then they were seeing how many electrons bounced off at different angles. Now, when you read this, you're wondering what were they doing. So an accident happened anyway, and they didn't intend to do this. So what happened is nickel is polycrystalline. Eh? So what happened is that some, I think, air entered and they had to bake this nickel. It is what? You guys have been doing baking in the lockdown. Eh? Kufumba cake. So what happened is that they were doing this baking, and what they didn't know is that nickel itself is polycrystalline, but as they baked it, the lattice became regular. So you had so here I was saying it is polycrystalline. That means it is polycrystalline. So you can say it doesn't. It's not like a crystal. The crystal has regularly spaced atoms, and these atoms you can know. And these layers is. So they are usually spaced by distance d. Now, in between, so layers of atoms form what you call, I'll say layers of atoms, but they form what you call lattice. Sorry about that. So layers of atoms form lattices, but lattices can also be just the arrangement of the atoms, as long as you have a regular structure or certain repetitive structure. So when an accident happened, not like the Compton thing, but air entered the vacuum and then they baked this. So they heated it up in the temperature oven. So to get out that air. Then, so in this bit, it created large portions of what? Large portions of a crystalline structure. So the oven is wrong, but that is the crystal now. So I don't know if I want to call it baked crystal, but so it is nickel. So that is important for you to add there. Using regular nickel will have regular reflections. Now, so as these guys were doing this, this is a 3D rendering in iceberg. Iceberg goes on to, I've switched to iceberg briefly, but it's not a good thing to know. But it has that, it sort of tries to derive that expression for rest mass. But again, it also refers to an appendix. We'll be fine. And then there's a sort of different derivation based on resolving these angles. Now, we don't have time, but you can also resolve these vectors into angles instead of using that cosine rule. So resolve them, and then you'll end up with the same expression. I think, yeah. So this also gives a very good graph of what happens with delta lambda with angle. So pi is 180, pi over 2 is 90. So delta lambda increases, and its maximum at 180. I think we talked about that as you're answering questions. So already X-ray production is a reverse. I'm going to that. I think let me just search for it. Davidson Davison gamma experiment is page 56. Let's just keep searching. So, yeah, so this one was working alone, and also gamma was working, but then they were sharing notes using the same apparatus. Sorry, they're using the same apparatus. I think the microphone has been down. So this is the setup we prefer to use. So this is the crystalline nickel, and then you have that filament generating electrons. Now, in between what you have here is a focusing grid. So you have it does both focusing and it determines the speed of what of those electrons, because it sort of attracts electrons, so it accelerates them into. So the first portion there is an electron gun. So the next question, what you call electron gun? This was my rotating thing. So that bit which is highlighted is the electron gun. Then the other bit is the accelerating. Oh. No, I don't want the hand. So this is the electron gun, and then that is the bit that the whole focusing of the electron. So this is your nickel. So crystalline nickel. And what happened is what is interesting. So you don't have to follow for part 2. We're going to see what exactly happened. So they put this detector here and they were trying to detect at different angles. So this is not the same angle as compound. So they just had this detector here at different angles. And what they're able to observe is something interesting, that the peak, this detector for every, it magnifies the impact of like one electron. So you can be able to, it's like how you have the Geiger counter for radiation. So it does that, does that, does that. So you have those different angles. So there's an interesting graph which they saw, which was interesting. So before you expect all angles to have, I'm trying not to say OMG, but it is shifting up. So for usually, classically, you'd expect that on a regular surface, all angles will have the same intensity, the same current, or you'd have either the same or some typical variations around that same current. So what you don't expect is having this peak here. So that peak is as a result of something which was which is called Bragg's reflection. Now Bragg's reflection is when X-rays are scattered within this crystal, you have this Bragg's law, n lambda is equal to. So the Bragg, we call it Bragg relation, sometimes called Bragg's scattering, Bragg's reflection. I don't know, people have named it very many things, but let me just check, because Bragg's reflection is a real thing. It is not the bragging you guys do. It has an extra G on it. This has more swag. So it's called broad reflection. So I'll just go back. Man, let's change my language. So Yandex, that are you? Okay, let's go to this PDF here. You should have it. So this is your Nico. It's like upside down. So what happens is that you're looking at one wave. Again, I have to go and look for the pen. Kaliwa. How do I change its color? It's not in the comments. It comes with one color. So anyway, I'll do it from here. So you have a wave. It interacts with that crystal. I'll just use the atom point. So you have an incident angle and you have a reflected angle. All right. So the reason you see these points, it's actually this lattice which refracts. It's not the atom. So as long as this wave is touching that, I should add another color. But I don't have time to go to paint. So as long as that bit is touching the lattice, it doesn't have to touch the atom. It's the lattice that does the refraction. But it is a property of the spacing of these atoms, which is, I need to write slowly, which is D. So in between that you have D. So D is the separation of the atoms. Then, so all wavelengths, so n lambda, remember the allowed modes, so it is something similar to that. So it is 2D. So I need to write really slowly to be able to write something. 2D sine. To be sine theta. And theta is the same, it's the angle between this, between the wave and the what? And the plane. You remember we said it's the plane or the lattice which does the diffraction. So so this is between the atoms, but you see this D here. So you can call this dA or D prime. Let's just use D prime. So that, because we're using D here. So sometimes it will be letter A. So it's not the spacing between the atoms, it is the spacing between the lattice that creates that reflect. So Braggs reflection is actually what you call it. You can guess the one, diffraction. So waves undergo different properties. Some of it is reflection, some of it is refraction, and then you have diffraction, which is with D or delta, DIFRACTION. Competition. So that Bragg's diffraction is what brings us here. So an explanation of Bragg's law in your notes for those who have forgotten and need to go by it. So it says, in essence, this wave is incident. Use the atom as a point, but it's really incident on the what? On the lattice, as long as it has a contact point on the lattice. That is where you have. So the path length increases by 2d sin theta. etc. So that is Bragg's law. So that is Bragg's law. And then we go back to this. So you have the two peaks. So you have this major peak, and this peak depends on the accelerating voltage. So why does it depend on the accelerating voltage? It is good you asked. Now, you remember we said that K is a half mv squared. The energy of when I told you to look at the diagram, I was emphasizing a lot the accelerating bit. The diagram should be up. Let's call up. I was emphasizing this accelerating bit. Now, you know that if you accelerate an electron or a charge, any charge, we can see the charge is E. And you accelerate it through a charge, voltage V. This gives you the what? The energy that particle has gained. Because E is the charge, P is the what? And V is the potential difference. So even electrons, once you accelerate electrons into by voltage V, which you see here, EV is equal to the energy. Now for an electron, I mean sorry, unplug the charger. For these electrons, the energy they gain is going to be proportional to the accelerating voltage. And so you can get different turbos using different voltages, but we're going to see how. So this energy is equal to I mean, energy that you gain is equal to E times the charge that you have and the potential by which it has been accelerated. And remember that E is also equal to momentum times speed of light, PC. And you know should we do it here? And you know P is equal to lambda is H over P. So P is H over what? H over lambda. So it will become HC over lambda. So you can, from here, we can get lambdas HC over E times V. So is HC over E times V. And those expressions for so EV is kinetic energy, so we can get velocity and what, but so here we have seen that lambda is inversely proportional to 1 over voltage. So as increased voltage, lambda smaller, so we'll attempt to have that with this. As you increase voltage, lambda becomes small. As you reduce voltage, your lambda becomes bigger. So it comes from this bit here. Number 2 is equal to n sine theta. So these questions are typically straightforward, but you need to know that phi is the angle between the lattice, not between the atoms. And you also need to know so, you have that bit. So we can get the wavelength for that 54 electron volts, and that we use this equation over here, equation 3-2. Equation 3-2 is that one. We substitute it into right? Yes. Times V, yes. So this is HC over P, EV, something was just off. So this is P is MV. So we can use kinetic energy. Because the energy gained by electron, the one of concern is kinetic energy. So there should be an explanation in there. I can just show you. Okay, sorry about that. The screening was a bit intense. Lambda is P over MV, yes, but where's the accelerating voltage? So just a recap, you have the heated filament, which we saw in icebergs, so which is that bit which has the heating coil. So that heating coil generates electrons which are focused by this, and then they hit this, and then you're able to see different angles. And for this particular voltage, you have T4 degrees. Yes, this is the expression, aren't it? So this energy is given by It is half mv squared. It's actually here. That half mv squared, mv is the momentum. So if you multiply through by m, right? So it becomes m squared v squared, half m squared v squared is equal to E, where E is energy. So and that mv becomes what? Momentum. So EVB is the momentum squared over 2m, so you can get momentum by twice mass times voltage, then the square root of that. So yeah, the questions seem to be interesting around there. So this is where the confusion usually comes in. In terms of the atomic spacing, this is the spacing between lattices. It is not the spacing between atoms. This is not clear. So here you have a cross section of these articles forming this lattice. So next time we'll look at de Broglie's hypothesis. We are going, because we have already looked at the Davison gamma. Maybe the one other, okay, what I've been trying to emphasize is that different voltages will give you different peaks. Voltages will give you different peaks. So next time we'll look at de Broglie. So to Hugh and Young and read through de Broglie. And de Broglie's hypothesis was radical. De Broglie was a historian, and then he wanted to be a diplomat, like an ambassador. Well, that's what his family thought he would be. But he got spoiled and decided to do physics with his brother. So Maurice, so Louis came in and then joined Maurice. And then he PhD from history to physics. So it's always not too late. So he got interested because every time Maurice would come home, he'd be like, we did this. You guys are at home now, so maybe every time you're talking about engineering, so your sibling is like, what is hard about this engineering? But in this case, this guy he had already planned to enroll for a PhD in history. I think he had started, then he switched to this stuff. So look at, you guys will look at the electron microscope. I'll just give you a simple assignment on that. You've also looked at it before, so it's not new, but there are attributes which we'll discuss about it that we named. So any questions? We should be closing today's session. Mr. Mukwai, do you have any questions? Or Mr. Kariuchi?
Yes, sir.
Karaoke's picture, karaoke, his account picture is, I think, for somebody else.
I just appreciate your Just appreciate your service.
Okay.
As well.
Yeah.
I appreciate service. But the Google Meet thing is Google Meet is a little disturbing. It connects and disconnects then, but I have a suggestion that maybe the next meeting use Zoom.
So had its challenges as well, because once I disconnect, everyone goes off. That is its biggest challenge. But I think for this this bit, you need to learn how to pin the video, because what you think is a disconnection sometimes is an unpinned video.
Oh.
But every time you leave and you join,
I think Google Meet is better because
so some people are
Excuse
being
me, sir?
confused. We are being hosted by Mr. Aaron. So that is his account. That is why you see the presenter is Aaron. Somebody was saying, excuse me. So we have 20 other, unless you guys want to take like a 20-minute break, because it is not easy to have this. So on Monday we should be for 1 hour. Usually I wanted us to have like one session a week, but we still have stuff to cover. So the glory, and then we'll do a wrap up of the concepts around this, and then after doing the wrap up of the concepts, then we can look at the uncertainty principle. So after uncertainty principle, we should be diving into Schrodinger. Then after Schrodinger, so yeah, basically we have finished atomic theory. After atomic theory, we have lasers and superconductivity. Okay, so I'll have this recording posted later on. I'll share the link first. I'll share the link to the recording. Then I'll see how to, if the size is less than 200 MB, I can have it on. If it's not, we might have to maybe edit or something.
Excuse me, sir.
Yes.
I went to Mwere and they asked me for the enrollment key. What is that?
Now, I've not yet enrolled people to the course. I've not yet enrolled people there. So I was explaining at the beginning of the meeting that I needed for people to first of all be in touch with the class reps as far as, okay, some of you just fill the form and put in your details, but even that step is important to know immediately how people are being reached out to. So the next step, I think the class should try and see who hasn't yet filled in on their part, and then we see if we can be able to reach those people. If it is a communication issue, if it is issues, also we need to see what sort of support we can be able to have. Okay. Tugenda kukoma wano leero. The only way you can continue is if we take a break. Because
Before, sir.
Yeah.
There was a question here
Yes,
that briefly, why the classical physics fail to account for the Kopplung effect?
Yes. So what bits of does the classical physics fail to explain? We need to give the observations and where it fails. That is what the question is asking. Trying to look through the chapter beginning. So there are a few other experiments there which we don't look at. Can send it to you. But some people have also looked at the double slit experiment. The double slit experiment, there's Mr. Quantum. Mr. Quantum is a cartoon. But we'll do that when we're looking at the write-up. Mr. Quantum. Okay, it's not a cartoon, it's an animation. It's difference. But why is it? Does it go to English? So we'll look at this duality later on. Look for Mr. Quantum. I'll just share that link. So in our wrap up, because we have seen that electrons behave as particles and they behave as, okay, electrons are particles already, but they behave as waves. And we have seen that light or photons, which are waves, also behave as particles. So this is what we call the wave-particle duality. And are they both? Are they either? Are they all? Then what is exactly happening? How do we know which property that we're going to look at? How do you know what we're going to expect? So that is where we look at, where we see Mr. Quantum. So that's the link over there. Yep. So it is true, Zoom has screen sharing features, but this one you have to pin, but you can zoom, you can zoom into the content. Sometimes you need to change the orientation of your device. If you're using a phone, just make sure that it rotates, because if you do that, then it's able to rotate. Okay, guys, I think we can have a good week. I already see most people have dropped off. So about 25 still remaining. So greetings again to Mr. Ogola, who has been today's one of the students. Yeah, so see you guys on Monday.
Thank you very much.
So on Monday I'll try and enroll you.
Thank you, sir.
Yeah, so in between now, just go through the examples. You can have discussions offline on WhatsApp with yourselves, and then make sure you're not lagging behind, because the things are, you might have that tendency to lag behind. Okay, bye-bye, good.
Okay, good day.
Let me first see how recording. Okay.